Welcome to this lecture where we'll be taking a look at the measures of position. So we are going to be looking at the different types of fractals. And when we talk of fractals, we are simply talking about partitioning numbers or dividing numbers into other data sets. Okay, we are going to split numbers into equal parts. So the first one we will be looking at quartiles, then we'll have time to look at deciles and then percentiles. So what are quartiles? Quartiles, when you deal with quartiles, you approximately divide an ordered data set. So when you have your data set, you first of all have to order it in ascending order of magnitude, and you split it into 4 equal parts. Then you have the first quartile, which is approximately 1/4 of your data, or 25%. Now, given that you've already ordered it, it means it's the first 25%. The second quartile is about half of your data. It falls below that. In other words, we are talking of the median. And the third quartile, you are looking at 75%. And then that's it. Let's take a look at this example to make sense of quartiles. So we are looking at quartiles. It says the number of nuclear power plants in the top 15 nuclear power producing countries in the world are listed. Find the first, second, and third quartiles of the data set. So the first thing you need to do is to arrange it in ascending order of magnitude, and then you start splitting it into 4. So what we've done is we've arranged it in ascending order. And the first thing you want to do, you want to look at the lower half and the upper half. So when you arrange it in ascending order, you look for the median, okay? Now, we have 15. It means we are dealing with an odd number. So you are looking for the first 7 and the last 7, and the middle part is simply the median. So this simply tells you this is the lower half and this is the upper half. Now, how do you look for the first quartile? So the first thing, you split it into 2. You look for the median. Once you have the median, it means you have the lower half and the upper half. Now, when you come to the lower half, you now look for the median of the lower half. That will give you the first quartile. You have the second quartile, which is the median. And then you look for the median of the upper half, which will give you the third quartile. Now, if you take this data set, just take a look at it. You are dealing with 1, 2, 3, 4, 5, 6, 7, which simply tells you the fourth data point is the first quartile, second quartile. You do the same here, 1, 2, 3, 4, 5, 6, 7. So this is the third quartile, Q1, Q2, and this is the third Q, which simply means from there you can compute what we call the interquartile range. The interquartile range is simply the difference between Q3 and Q1. So basically, that you can use it to interpret. Here you say about 1/4 of the countries have 10 or less. So 10 or less nuclear plants. Then you can say about half of the countries have 18. About 75% have 31 or less. So that's how you approach it. And the interquartile range, now remember, we are talking of a range. In other words, we are looking at the distance from here to here. Okay, the range of nuclear plants. So how do we go about doing that? Given that the third quartile is 31 and the first quartile is 10, when you do the math, which is simply Q3 minus Q1, you end up with an interquartile range of 21. So you can say the number of power plants in the middle portion of the data set vary by at most 21. So it's simply a range. Now, the knowledge you are taking from here, you will be using it. So it's very important for you to fully understand the concept of quartiles, because when you come to a plot as the box and whisker plot, it helps to show that graphically, because you will take a look at the minimum, the max, first quartile, median, and the third quartile. So you have one plot that automatically shows all of that. So it's extremely important to be comfortable interpreting the concept of quartiles because it will help you interpret this 5-number summary. And at times it may also show you where outliers are. So let's take an example to make sure it's clear. So this is your box and whisker. You have the minimum, you have the max, you have the first quartile, second and third quartile, and your box is your interquartile range, which goes from Q3 to Q1. That's your interquartile range. So if you take the data set we've been using, so you'll find that your minimum is 6, max is 104, your Q1 is 10, Q2 is 18, and this one is basically 31. So your interquartile range will be 31 minus 10, which is 21. So basically the distance from here to here is 21. And you can clearly see just from this plot, you can clearly see what we're saying. So about 25% of countries have just 25 or less, have 10. About 50% of them, 50 or less, have 18, 75% or less have, and here you have some extremes. Okay, so let's move on. Here you have the most popular different fractals, which the concept of fractal has to do with splitting your data set into equal parts. Here you are splitting it in 4, here you are splitting it in 10 equal parts, and here you are splitting it in 100 equal parts. So the quartiles you divide into 4 equal, 10 equal, 100 equal parts. Now let's take a look at this example of a percentile. For the percentile, we generally use the cumulative, or what we did a few lectures ago, it's the ogive. Now the ogive, you are not using the frequency here, but you are using the relative frequency. You have the score, and here you have the relative frequency. So if you've forgotten, I think it's the first or the second lecture, take a look at it. And in that lecture, we took a look at the ogive. So the ogive represents the cumulative frequency distribution for SAT score. So this is the data set, and it's simply showing what's going on. So what test score represents the 62nd percentile. So you can take a look here, and here you have the percentile because it's split into 100, and you can see that around here you can see what goes to that point. So you just need to intersect 62 and see what's here. It's going to tell you the score, that the score is whatever it is, about 1600 or less. That's the idea behind it. Now let's take a look at the last concept under this. It's simply the standard score. Now the standard score, in order for you to standardize a score, you are first of all assuming that the data set is normally distributed. That if you plot the histogram, you will have something that looks like the bell shape. That's the first assumption. When that assumption holds, you can simply standardize it using this approach. So what do? You simply divide the deviation by the standard deviation. That's all. So here we are looking at a particular value and the mean value. Now, once you have that value and the mean value, remember this is your deviation. You are looking at how that particular score deviates from the mean value. And now you are dividing it by the standard deviation. That will give you the standard score. Okay? Whenever you have to compute the standard score, look for the deviation and then you divide it by the standard deviation. It's going to give you your standard score. Let's take this example. It's looking at different actors. It says blah 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 won the Oscar for best supporting actor at age 29 for his role in the movie The Dark Knight. blah 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 won the Oscar for the best supporting actress at age 34 for her role in blah blah blah. The mean age for all best supporting actor winners is, so here you are having the mean age for all. In other words, this is the population standard deviation, which is known as mu. Mu is your population standard deviation. X bar is the sample standard deviation. So in this case, we are using the population standard deviation, which has been given. It says for all, not for a sample. So, and the standard deviation has also been given. So if you know this value, you know this value, and you know the mu, you know the standard deviation, it means you can compute the standard score for this person, and also the standard score for this person. You can do that because you have the mu and you have the standard deviation. So here we are saying the mean age of all best supporting actresses is this. So this is for the actors, these are for the actresses with the standard deviation of that. So let's compute and compare the results. So if you do the math, you'll see that for the male actor, you have 29 minus, this is the mu for all male actors and the standard deviation for male actors. You see that he appears 1.9 standard deviation to the left of what we have of the mean value. Okay. Meanwhile, Penelope Cruz appears 0.42 standard deviations to the left. And that is it. Voila. So anyone who appears more than 3 standard deviations, be it to the right or to the left, that is a very unusual value that looks like what we call an outlier. Now, if you appear more than 2 standard deviations to the left or to the right, it's still very unusual, and the usual scores are the median score or 1 or 2, 1 standard deviation to the right or to the left of what you expect. So the concept of deviations just help you understand what is usual, what is unusual. If your grades in class, if you have a grade that lies between 1 standard deviation to the right or to the left of the class average, it's a usual score. So it's not a problem to have below average as long as it's 1 standard deviation to the left or 1 standard deviation to the right. That's a normal, that's usual. But once you go 2 standard deviations, it becomes unusual, and more than 2 standard deviations to the left or to the right, that's a very unusual score. It simply means something special is happening. And that will be it for this lecture. I'll see you for the next one. We'll move on to a next topic.